Alrighty, so here's the Chapter 12 discussion, problem solving and debugging. The remainder of the chapters, Chapter 12, 13, 14, and 15, are all related specifically to programming and will be towards the programming nature. So we're going to talk about different ways of problem solving and how problem solving in this case can be approached from many fields. Specifically, we're going to look at almost like a scientific method for debugging. There are, at least in this book, in this chapter, what they call 13 rules of debugging. And we'll see some of those. A lot of these are really good. A lot of them are old. So as we go through these 13 rules, I'll tell you which ones that are really helpful and others that maybe not so helpful or maybe a little bit more outdated. And then as we talk about that, I'll try to bring in some of the newer methods for debugging. However, debugging or problem solving is a pretty good discipline. Following these approaches, at least you'll get a good solid foundation of how to look at problem solving and debugging. So, computer science, defined as the art and science of developing solutions to problems. Key word here is right here, art. So just like any kind of art out in the art field, it is subjective to personal experiences. And so when you are coming to a solution, it is coming with your background, your experiences. It may be new, or you may be a seasoned developer. And so in my opinion, it's really important. This is really important because the more people you can get input from on a solution, it seems to me, at least in my experience, that the better results we've had in getting a product that appealed to a wider audience. Meaning that, you sit down, you come up with a problem, or a problem is identified, and you go at it alone. You're using your experiences and your background and history to solve that problem. And while that is perfectly acceptable, because that's how we all live our lives, it may be a narrower view than what's needed. As a developer, I know that I'm more utilitarian. If they ask me to develop a solution to a problem, I'm going to give a solution to a problem. It may not be pretty, it may not be good to look at, but at the same time, it will get the job done. And that may not be 100% of what has been asked. And so the more input and more culturally diverse input I've found, both genders and in different people who will be using the software, the better you're going to have it. And then for debugging, it's finding and fixing a problem. There's an old adage that you write code 10% of the time and debug 90% of the time, which not necessarily true, but it does seem that that's what's happening a lot when you're programming, is you'll get a solution and then you'll find a problem. If you're lucky enough to work at a company that has its own QA or quality assurance department, their job is to find bugs and to bring them back to you. And a lot of times you'll look at it and go, oh, that's, it's supposed to add two numbers together. Why'd you put letters in there? But that's their job. And so you will go out and you will find problems. Some problems you'll be able to fix right away. You'll look at it and go, oh, yeah, I should have done this. Others can take a long time. There's a lot of tools out there that you can use, but a lot of it comes with knowledge and experience. So my recommendation as we get into the debugging part of this is, after you've given it a good attempt and you've gone about as far as you think you can go, ask questions, whether it be out online, whether it be with other developers. Don't sit there and bang your head against the wall. It's the most frustrating thing in the world to try to debug something and not get anywhere. Sometimes you can ask a question and the person will say, hey, you know what, I ran across this a long time ago and here's this obscure thing that fixed the problem. I know it's happened to me, and so don't be afraid to ask. So we talk about the mental game of problem solving, and it really is a mental game. I like to think that when you're developing a software solution, that you'll spend hopefully 60% of the time figuring out the solution before you write any code whatsoever, and then 40% of your time coding the solution. Development tools nowadays, and I use Visual Studio a lot as an example because I use Visual Studio a lot. Visual Studio has a lot of tools to help with coding, banging out code as they call it. And so they've kind of changed their focus now of spending a lot of time writing lots and lots of lines of code to getting the job done. So you're going to want to spend a good majority of your time actually thinking about the problem, finding out what the solution is that they're really after and ways to get to that solution, and then start writing your code. So in the early 20th century, we're actually going to talk about the scientific methodology here. People kind of got out of the tinkering in the back garages and started using laboratories and using specific methodologies to be able to repeat over and over and changing things to get a different result, and really notating what they're doing, writing down what's going on, observing, adapting, and changing. And so the big focus in that time was stripped down to math or logic problems. And so this is a big reason why, if you go into computer science, they have you take a lot of math classes. You're not necessarily going to be doing a lot of math programming unless you're getting into the scientific realm, or you're getting into maybe AI, or you're going to do low-level developing for graphics. But a lot of the time, the computers have built-in objects and classes for you so that you don't have to do the math. The reason why we're giving you the math is to think logically. And that's what you need to do on problem solving. Is you have to have a logical progression, and that's what math teaches. It's logic. It's A B C D instead of A X W, jumping all over the place. You can eventually get to a solution that way, but if you do it logically and systematically, you're going to have better results, and in the end, your debugging is going to be a little bit easier. So then in the 70s, they moved to specific problems and kind of push things out into domains. And if you look back during that time from the early 20th century, the 70s, that suddenly a scientist wasn't able to, just be a scientist and know everything. Chemistry, math, physics, all these fields started becoming specialties because it became more and more complex and more in depth as they continue to look at the problems and solve those. So it was focused less on finding general problems and finding very specific problems. And that's kind of where we've moved today. A general problem in the old days could have been, to make it topical, could have been, hey, we need to find a problem with all these infections. And, through trial and error and a little happenstance, they found penicillin and found out that it kind of was what they call a broad spectrum antibiotic and did a lot of things. Well, now they're very, very much in tune with specific bacteria and different antibiotics for that. And so it's now more of a specific problem solving. And a bit of advice I can give, everybody wants to be a developer, but to be a really good developer, you need to take some time and as much as you can find out how the organization works. What's their methodology? What's their business rules? What's their underlying engine that keeps things going? Understand how that works. Maybe not in depth, but at least have a good understanding of it so that you can then solve problems within the framework of the company or offer suggestions. Become more focused on that company, you'll become a more valuable resource. And so also, the key discovery reorganized and included study of intuition and emotional roles in problems solving, which is important in the way that your gut feeling, so to speak, you've been programming long enough, you kind of have a gut feeling of what you think may be the problem. And that's important because as you're sitting down in front of a program and you see bugs coming up or errors are being thrown, that intuition, that experience that you have you could say, that looks like it's a database connection issue. So now you can focus in on that and either find the problem or eliminate it versus just trying everything haphazardly. And then, of course, experience comes in. Um, you're not expected out of the gate, nor should you be expected from a company out of the gate to be able to debug everything on the fly right away. After a while, you get that intuition, you listen to it, you get that experience. Big thing is like I was saying earlier, if you run into a problem you've never met before, you try to solve it, and then you go ask someone, they may have had experience with a similar problem. Hey, in my last company, this is what we found happen, and this might be a good solution. And sure enough, it helps. So again, don't get frustrated with it. Don't expect to know everything about it because that's not the way it works. So really, you just need to have patience, and you need to, have the inclination and the tenacity to solve these problems. So this is a game. It's called the Tower of Hanoi Puzzle, and this is a classic mental game of how many steps it takes to move these disks from here to here. And there's certain rules. So for instance, these disks, you cannot stack a taller disk on, a wider disk on a narrower disk. So this disk here would have to come here, and then you would move this disk over to here, and then you'd move the small disk here, and you would continue to move these and shuffle them back and forth until you get this stack just like this over here. And it's a logic game. And I encourage all of you who are getting into programming to go out and, with your language of choice, go out and find code for this Tower of Hanoi puzzle, because it teaches logic. It teaches you to show how to think and say, okay, I have a set of rules here. How am I going to accomplish my goal within those rules? And it's pretty amazing. There's contests out here. I don't know if they're doing them anymore, but there were contests out there to see, what's the fewest number of steps to move this from here to here, and the tightest code, the fewest lines, etc. So this is something that I encourage you to at least look at. This is kind of falling out of favor, but it's a great logic puzzle to look at to solve. It's not a requirement, or it's not, for the development project. I'm not going to ask you to do a Tower of Hanoi puzzle because it is pretty complex, but it should be something that you explore further, just to look at how the logical progression moves. So, very first one, I move this to the very first problem-solving mental game task is stay positive. It is very easy to get discouraged while you're debugging something, especially something really complex. It says boast aloud or visualize or even write down positive results. And that's, it sounds kind of hinky, but it does help, because as you're going through and you're saying, well, I solved this and I solved this, then you get to a problem, you can overcome this problem. It may take a little bit. When you're done with that and you have solved the problem, whether you did it yourself or somebody else helped you, write it down. Keep that with you, because it is, first of all, an accomplishment of something you were able to get done. But second of all, it's great reference to go back, and when the next person comes by and says, oh man, I'm having this problem, you can say, hey, I got a solution for you. And then you are able to help the next person. So think positively about it. I tell you from personal experience that, I've been discouraged debugging. I've gone home some days having tried to solve a bug that just I couldn't seem to wrap my head around. But I was still positive about it, saying, if it's there, we can fix it. If we can't fix it, we can find a workaround for it. If we can't find a workaround for it, at least we know what the problem is and try to anticipate it. There's a lot of things that we can do. I have worked with people that every time there was a bug, it was like the end of the world, and they would just wail and they would be so upset, and it was like never ending on their complaints. And honestly, working with someone like that after a while, it really wears on you. You know, be patient. Debugging takes time, especially when you're just starting out with it, or you're starting out with a new language, or you're starting out with a new process you've never dealt before, or you're starting out with, new classes that you're using that you've never used before. It takes time. And as computer programs become easier to develop in, they can also become complex. So don't really compare yourself to the person next to you who may have 5 years or 10 years, or somebody who's been at the company a year and knows more than you do. Be patient. And I don't think it's fair, and I really haven't seen this a lot in companies. It used to be that everybody was expected to debug at the same rate, but now people understand it's complex. The big thing here is, again, be positive. When you go to ask for help, say, hey, these are the things that I've tried, and none of them seem to be working. Just don't go to somebody and say, oh, I can't get this done, this sucks. Then people aren't really going to want to help you. But go in and say, hey, this is the problem. Here's a couple of things that I've tried, and I just can't seem to get past it. A positive attitude does affect your environment. So, why are problems so hard to solve? Well, we have these 5 categories in here, which are kind of generic categories. A problem might be easy to solve, is what it says, depending on the underlying cause. It might be something as simple as, hey, I want to add 2 integers together, and I want to make sure they're positive, and I got a negative integer in there somehow, and so now I'm, instead of charging people tax, I'm subtracting tax. If you've seen that show Office Space, which I really love, in there, they, just as a little background, they write a virus to get back at the company because they're getting fired, to skim fractions of pennies out into a count, that they say it just rounds down, and those pennies are kind of lost, so they want to capture those. And so in a couple of days, they go check out their bank account, expecting there to be, maybe $5-6, and there's like 6 figures in there, and they're freaking out in the car. They're talking about it. The guy goes, oh, I must have missed a comma. I always do something stupid like that. And although it's, hilarious in the movie, it sometimes can be a semicolon or a comma or a period. I do know that in one of the accidents they had to abort a mission, it was because of a comma or a period in the wrong place. Those might be easy. However, there are some that are hard, and they are really hard. These could be multi-threaded debugging. You could have problems with the underlying operating system. You could have problems with a database or reaching out across the internet. There are some things that are going to be hard because you don't have a lot of control over those. So, it's people want to triage a bug, and that would seem to be the thing for a long time. We need to triage this bug. And triage meant that you take a good stab at it and say, well, I think it's this or it's that, and you end up, making a best guess, saying, well, on a scale of 1 to 5, this is a 2, and then it ends up being a 5. Again, that comes with experience, but ask questions. So we have 5 debugging. You got coding issues. Those are generally the ones that are easy to fix, like I told you. They say not understanding the programming language thoroughly. That's not necessarily the case. It could also be that you're programming in multiple languages, and you sometimes, start writing another language in your language, or you forget a semicolon, or you forget to add 2 numbers together and, to return a positive value. Those are easy to fix. Those are just, I used the wrong method, or I didn't close with a semicolon. The nice thing about coding bugs is a lot of times they're caught now in the GUI. So for instance, in Visual Studio, if you forget a semicolon, you'll get a little red squiggly line. And that's a real huge help now. So a lot of these coding bugs that used to be able to slip by, you can now catch before you even try to compile it. A lot of times coding errors can be caught in compile. So when they compile the code, it comes up and says there's a syntax error. But if it does get by that it's not a syntax error and you have an unintended consequence, then you can look at that and go back in and say, oh, I was supposed to, use this method and I used this method. Again, those are relatively easy to find. And then you get into logic bugs, and these can really be a bugger. The example they have here is a counter going past the end of an array, getting an out of bounds memory exception. Well, this happens if you, like, for instance, have an array of 6 items. Remember, arrays start at 0 and go to 5, and you try to access the array on the index in position number 6, and so it gives an out of bounds memory location. Now, there's a lot of ways in the programming language to avoid getting an out of bounds memory exception. For instance, using an index counter, or if you're in a collection of objects, you can do a for each to make sure you're not getting out of that array bounds, and that's a good example of a logic errors. But there's other logic errors that are more difficult to fix. For instance, if you're doing complex calculations, for instance, where I was working at Lifetime, I helped write the shopping cart application, and these guys at Lifetime had hundreds and hundreds of these codes that people can go in that would adjust the pricing or free shipping. There's all these coupons that were applied, and I mean literally hundreds of them. They were all active, and we had to go through and we had to test those, and for some reason a couple of these codes would always give the wrong answer, and it was so hard to figure out what the problem was on these logic bugs because the code appeared to look the same. And what happened is that when they were putting in a couple of these coupon codes, the mathematical order of precedence was wrong. They had missed some parentheses. And so what was happening is it was multiplying the tax to the total and then taking off the complete 30-40% off after the tax was added. And so taxes weren't being collected right, and it took a long time to figure that one out. And so logic bugs are not necessarily something that jump out at you. It can be something as subtle as order of precedence. So bad data bugs, these are something that you may be able to control, but sometimes you can't. So for instance, you have people, outside vendors, who are sending you information, and you tell them, I need this information in this format and with these data types, meaning I want decimals, or I want currency. I don't want point, $10.10, it'd be 10.10, not 10.10853, a floating number. And so they can give you some bad data, and a lot of times you can't control that. And so you have to do a lot of validation or transformation and to help control that, to make sure that the data comes in. But that's like an external customers. But you can get bad data inside too. And bad data can come inside your program because another logic bug somewhere down the line wasn't caught, and that bad data is getting written out to a database, for example, and then you pull it in to work on it again. And so a lot of times what can happen is you'll spend all this time figuring out why this bad data is getting in there, and then not tracing it upstream and realizing that the real bug, and this is the key, the real bug is actually in another method somewhere doing something wrong. And again, that's the art of debugging, saying, where is this problem really happening? A lot of times it doesn't manifest where the bug happens. It may pass downstream for a little bit, and then you have to use what they call the stack and kind of go back and look at all of the data or all the methods that this data was touched until you get to what you think is the problem, and fix it from there. So compatibility bugs, these are less and less of an issue now. Used to be compatibility bugs were quite a problem. At least with .NET and .NET Core, you can write an application in .NET Core and expect it to run in Windows, Mac, and Linux. Java was purported to be that, but it ended up being write once, debug everywhere. And in that, what you could write and say, well, I'm going to write this for a Windows application, and then you try to put it on a Macintosh and it fails because you have some compatibility issues. These have become really good at the open source movement has helped this. But a lot of these companies have realized, hey, if my program runs on multiple platforms, that's a better solution than just making sure it only runs on Windows. It is coding bugs, and again, I don't know if I necessarily agree that it says understanding the platforms thoroughly could be a problem. Compatibility bugs, you may write exactly perfect code for all compatibility, but you don't have control of, say, someone has made a modification to an operating system, a Linux system that doesn't accept that. So while it is a problem with understanding the platforms, it could be out of your control as well. And then you have architectural bugs, and this I left to last on purpose. Architectural bugs we're talking about here is the way that your system's set up. And it is not uncommon to go into a company, and this is a lot of companies that I've worked at, in which the solution needs to be presented now. And so a proof of concept is put together. And we talked about a proof of concept when we talked about the GUI development. So we have a proof of concept, and then what happens is they show it to the higher powers that be, and they love it, and they immediately want it to go into production. And so you put this proof of concept out there, and then you end up, instead of really writing it and architecting it the correct way, you just start doing bolt-ons and workarounds and patches, and pretty soon it gets so difficult to debug. The job I was at, the shipping company, was in this very situation. They had Ruby and PHP and VB Script and an old 20-year-old company that software they were using that was bolted in, that was very strong in databases, and then they had 3 different people using 3 different frameworks within the same program, and it was a nightmare. And 90% of the time that I spent the first 2-3 months was doing nothing more than maintenance and putting out fires, as they say. Hey, we have a bug, this new customer came in, so you fix that bug and you cause other bugs, and those bugs cause other bugs, and so you go in and look at the code, and there's commented code out that says uncommented this for this customer or that customer. These are horrible. They're hard to debug because often a small change in one bit of the code affects other bits of code that other people wrote and slapped together and managed to get together. So instead of having like a well-oiled supercar going down the road, you have more of a bolted together monstrosity where pieces are falling off, and as they're trying to change a tire going down the road going 80 miles an hour, because if you stop the car it's going to fall apart. So it says that it requires a complete code rewrite, and I've participated in those, but often the complete code rewrite is a really drastic step for a company, because what happens is they put out these processes and they've worked around them and dealt with them for so long that these proof of concepts have become in place, and the kind of the ecosphere that's gone around it to get through the idiosyncrasies of this code has now become standard practice. So then you want to completely rewrite it, and that will change everything, and then there's a cost because you still have to maintain that monstrosity that you put together. So oftentimes this will escalate over years before the company looks at it and says, we can't go any further because of all these problems that we have. This one here is where I now spend a lot of my time in my coding profession, is taking older systems, re-architecting, and figuring out how we can migrate to the new architectures, or what we could do to keep the other one limping along while we get the new one running. So, why is software difficult to debug? And again, I push this up to the very top. They call it the fog of war. Um, and here they're talking about it's difficult to see the internals and the logic, which can often happen. The programs I'm trying to figure out, I'm not a Ruby expert, so I really don't know what's going on in there. I'm just fumbling around trying to get things working, often doing so by mistake. But the fog of war also is you're so exhausted, mentally exhausted, from trying to keep this beast going while you have the, upper office yelling at you because they're potentially losing sale and money, and you've got end users yelling at you because their job is difficult or they can't do what they need to do. You've got other developers who are stressed, and so at a period of time there's a lot of burnout, and you kind of just get to the point where you're like shell shocked, at just the amount of fixing that needs to be done. And so, how do you get over that? Well, time and experience. You eventually learn to code faster. You learn how the company works. But my advice is don't do more than you can do. And it sounds like horrible advice. Well, what does that mean? Well, it used to be in the old IT days that, I worked once 36 hours straight. When I was working at the Ogden Standard Examiner, I was there at work 36 hours straight, because they had never not put a newspaper out except for once, and it was this prestigious thing, and it was an ego boost for the publisher of the paper. So I was young and I was excited, and we got in there and we worked 36 hours straight, and the whole time I'm thinking, oh man, at the end of this we're going to be heroes. So at the end of that, they got the paper out and they didn't miss anything, and I got, the publisher got a lot of recognition and congratulations, and I got, I think, a $10 gift card to a restaurant where the cheapest plate was like $30, you know, and after all of that, it was just like, why bother? Why bother working for you? Now, I'm not saying that you're there for, big bonuses or whatever, unless your job's tied to that, but it does help to be recognized. And when you're not recognized, and this war continues to rage on and on, you get to the point where you just become apathetic. And you just know, I'm going into work today, and it's the same old, your excitement's gone. And because of that, then you lose the desire to fix problems. And I've seen that. I've got friends who are no longer in the IT industry because they hit that point with some of their companies, and they felt it was unfulfilling and they didn't care anymore. Another big problem, and I kind of rank these in what I'm seeing more as a problem: multiple goals. You've got two people who want two different things that contradict each other. I was just asked in an interview question a couple days ago, what would you do if two vice presidents of equal power came to you and both wanted wanted their jobs done now? And the answer I gave was, well, I would look to see if there's any compatibilities between the two projects. But the very first thing I would do is I would say, did you know that so-and-so wants me to do this? Or do you know so-and-so wants me to do this? Oftentimes when you have multiple goals that affect or contradict each other, is two people in two separate areas not realizing that the left hand doesn't know what the right hand's doing. And so often you bring them together and they'll go, oh, I'm sorry, you're right, that's more important. Now it might get to the point where they're both going to fight with each other and you're caught in the middle, and you go to your boss and say, these two people want me to do these things, what do you want? If you are the boss, then you make your best call and then defend your actions. So multiple goals can really, really affect how you develop and why software problems come in. Especially if they both want them done now, you have a tendency to either try to shift your context from one project to another, which can cause problems. Anytime you shift context from one project to another, there's a ramp up time, and there's a time where you have to say, okay, where was I at when I was doing the previous job? And so that can get very, very frustrating after a long time, and it makes it so that it's difficult to keep on task, again leading to the fog of war above it, to the point where you're like, why am I even into this industry? So don't go at it alone. Use your boss, and make sure that they're doing their job by making them do the hard decisions initially. So complexity I put up there because computers, it's becoming easier to code, but the software itself is becoming more complex. And it says here, program may have many interrelated items with variation. So I want to kind of split this complexity into two parts. One complexity is you've got a program, your just program A, that instead of being able to be flexible enough to accommodate new customers coming in, for example, every new customer gets a small variation of that same program. And so now what started off as one program A, you now have program A and then A.1, A.2, A3, etc. that are all pretty similar, but just do something slightly different. And so now you've got these, every time a new customer comes in, you get a new problem. This is what was happening in my last job is, we have, this program, this is kind of, and was told over and over, this is the heart and soul of the program, but we have 4 variations because this person was doing this and this person was doing that. And it was just chaotic. And so it made it complex because then if we had to make a change, at first they would try to keep all of them in sync, saying, well, I'm making a change here, let's get them to the other ones. After a while they stopped, so there's a lot of duplication of effort. There was people doing coding in different ways with different methodologies, following a different set of rules, and it just became so intertwined that you had this same program with variations, multiple variations. On the other side of that is you've got a program that has interrelated items that are, now you're looking at not just client-server development or even end-tier development, as you used to call it. Now you're looking at a lot of web development, and you're looking at a lot of cloud development, and now we're pulling in AI to these things, and that adds some complexity. So every time you start adding these external systems for help, like AI in the cloud, or external systems you're communicating with, that notches up that complexity. And so now you have to account for, hey, I'm moving to the cloud. Well, what happens if the cloud's not available? What happens if this? So yes, it does give you the opportunity to store data in a reliable method, but now you've got a whole set of other things you need to look at. Is it available? How long are we going to keep a message on the queue, for instance? There's a lot of things that now that you're putting it onto another system that are out of your control that you have to try to account for. And then, of course, constant change. I have said over and over in the class, my advice for you, if you're a software developer and you go to work, is do not write one line of code without at least a defined set of requirements. It says your program characteristics change frequently. That is not necessarily a problem. Frequent change is kind of the nature of the beast in development in today's computers because things are moving so fast, and so it's not uncommon to start the program, at point A, and by the time you get to point B, a lot of things have changed. You've added more complexity. You've now said, hey, we need to add an app to this because we've got to have people on iPhones and Androids be able to get into here. Change is not a bad thing. What's a bad thing is your requirements constantly change so that you never even get a goal or an endpoint or a piece of software out the door. And so what can happen there is you can spend your time doing context switching to the point where you get so confused or burned out that you don't see an end goal, that this program's never going to make it. I was dealing with this at my last company at Visible. They would say, hey, there's a problem. We'd go in, propose it. I was always asking, can I get some assigned requirement saying this is the way it needs to go? I pushed for it to the point they said no, just get on it. So we started on it, and I would write up some requirements, send it off, and we get to the end, and by the time we've gotten to the end, it has changed. And so all that work we did was for nothing. I mean, it's not even salvageable. We're going in a different direction now, and we're going a different direction here. And some of the leadership there were changing directions when they read an article or on a whim or something else. It was really a hard place to work because all your time and effort, you never saw the end goal. And then you ended up spending a lot of times just keeping that old software running, and not being able to do any new development, not being able to get any new stuff done to help. And so, you know if your characteristics are changing frequently before you even get out the door, before you even get the program out the door, you're going to be spending a lot of time chasing your tail, never getting to an end point, and then eventually it may end up as, why aren't you doing your job? So my advice to you is, if you are going in to software and they're looking at this constant change, and you find that the requirements are changing on a daily or hourly basis, don't code, and just say, I need a defined set of requirements that I can program to. Have somebody send you an email saying, this is what I want, get a signature on it, and then start developing it. So then when it gets to the end, if they've changed their minds over and over and what you've delivered isn't what they expect, you can always bring out that piece of paper and say, this is what I was told to program to, and here's how this program meets these requirements. Otherwise you're going to find yourself really frustrated and wondering why you even got into this field. So there's a lot of problem-solving approaches, and some of these I'm just going to go over briefly, because I think some of them are kind of grasping, but the first one is definitely a good one. It's called a straw man argument, and a straw man argument is when you build up a theory or a problem, and then you tear it down, making it look like you're solving a problem when in fact the original problem was never touched. So it says here is you build up a problem theory knowing it will likely be knocked down, whether by yourself or somebody else. And it's called a straw man argument. This happens all the time. And you can put up something and say, well, I guess we could do this, knowing full well that nobody's going to go for that. This might be okay for what they call spitballing or blue sky, or you're getting together to try to come up brainstorming, etc. But when you're coming into a problem that's already been defined and needs a solution, really a straw man argument is, in my opinion, a show of somebody who either doesn't understand the problem or is not confident in their abilities but feels like they have to make some sort of a contribution. So a straw man argument might be, hey, well, we could always add, printing, and knowing full well that nobody's ever going to print for it, and they'd be like, why would you want to do that? But you felt like you've contributed. The next one is called heuristics, or rule of thumb. And this is something that comes with time and experience and just gut instinct, intuition, as we talked about earlier. It means that it's good enough. And good enough is there in is quotes. You can see that because good enough doesn't necessarily mean it's good enough for me. Is it good enough for you? We all have our different good enoughs. And so you can't necessarily say that this is going to be good enough for the company. But it's a good place to start. At the other side of that, you can get to a problem-solving approach. You can get it to the point where it's good enough, it solves the problem, but you always feel, I hear this, well, I'm a perfectionist, and so I want this to be perfect. Well, nothing's ever going to be perfect. And at a certain point, and again, this is experience, you've got to realize that this does an adequate job and meets the requirements, and I need to move on. Because just again, from experience, those people who sit there and tweak and tweak and tweak and get excited about a couple more milliseconds, often when it comes time for new assignments or if they need to let people go, those people are let go because they spend so much time in the not getting good enough code out that they're spending tweaking and so just as a piece of advice here, when you get to the point where you felt you met your requirements and over your experience, you can always look at it and go, well, I can prove that, and you may have a chance to go back later, or if you can improve the code substantially, you should. But if you get to the point where you're just like, well, if I just try this, I can shave off a little here or there, uh, at that point you're probably beyond problem solving approach, and now you're getting into I think maybe more of an ego boost. Now, in some companies I've worked at that were under regulation, for instance, Westinghouse with the Nuclear Regulatory Commission, we used the next one, the detailed checklist, and these checks had to be followed. And all of those checks had to be checked off for some of our software in order to be NRC compliant. And this made it easy in some cases because you knew that your software had to at least meet these requirements, not just for the NRC but also for the company itself. They had procedures for manufacturing that had been developed over 30 years that they still needed to follow, and these steps needed to be followed. And while it was very rigid and allowed for very little creativity, at least it was nice to be able to follow these procedures and say this software follows these procedures and the outputs are expected, and you had an end goal. It was kind of nice. So you have the scientific method, and I'm going to repeat this over and over. There is a question on the final about this scientific method, and you're applying what we used to think when I was going through a lot of my biology courses or chemistry. We always use the scientific method. We observe, report, test, verify, over and over and over. Well, you do that to some extent in software engineering as well. So the first is inductive reasoning, which is a basic approach to problem solving. So you observe what's happening. Now let's take this from the point of on these: observe, propose, test, repeat. Right? For software, this is a solution that needs to be solved, and the company comes to you and says, hey, we need this problem solved, problem A. And so you can take that and go and solve that problem, but to really to use the scientific method, you observe what's happening, meaning you may go out and talk to people who use the software. You may talk to other departments. You may talk to managers or super users. Maybe go out and see how they're using the software on the floor. You go out and observe how the software is being used and what the problem is. So then, doing that, you can propose a theory for why it's happening. Meaning, why are we missing orders? Why are we mismarking pieces of material? You go out there, you find these and say, hey, we're doing it because, I think we're doing it because, these people don't understand what these people are doing, or this software is, you just propose a theory. So you get the theory, and then you test that theory. How do you test that theory? You write some software to solve that problem based on your theory, and you test it. And you release the software, and does it solve the problem? No, it doesn't. Okay, go back. What did I miss in observation? Change your proposal, test that change, and you keep going until you get to the end result in which you think that your piece of software has been able to sufficiently solve the problem that you observed happening. So again, observe, propose, test, repeat. So these are the 13 I's of debugging, and I will put a 14th on there. I will say that these are not rigid. Some of them do make sense, and some of them I have either never used or don't understand what they're going with. But a lot of these are good. And there are test questions on these. So the 13 I's, you do need to at least understand what they are. And again, I bubbled this to the very top. I will own the problem. It does nobody any good to sit there and finger point what the problem is in software, or any solution really. When a problem is found, it is generally needs to be corrected, and time, effort, money, and resources are expended trying to point fingers, and at the end nothing happens. You get a bunch of people who are really pissed off at each other because they're all blaming each other. Beyond debugging, that starts to put rifts or contentions between departments. And the last thing you want is for the IT department to be seen as an enemy or a hindrance. So own the problem. It doesn't matter whether you caused that problem or whether it was caused by somebody else. You just stand up and say, someone says, we have this bug here. You stand up and say, all right, I'm on that bug. I will fix that bug. I am responsible for fixing that bug. That is what you say. I am responsible for it. And you take responsibility for it. It shows a sign of maturity. It shows a sign of leadership. And, as a problem solver, you want to get this fixed. The second one is remain calm. I've been in meetings now. There's stress. By all means, there is stress, and especially if a bug is out there and companies are losing millions of dollars. So there will be stress. But if you remain calm, you will think more rationally. When you're in a panic, you're not thinking rationally. Stress is not a bad thing necessarily, but panic is. If you're panicking, you're not thinking right. You're thinking, what's the quickest way to solve this, to get this off my back? And then it may give other bugs, or may not be tested thoroughly, or you may run up with a solution trying to say, hey, I got this fixed. I think this is going to help it, and it makes it worse. Remain calm. Take a couple of deep breaths. Sometimes it's best to get up from your computer and take a walk. Use the scientific method for solving approaches. Scientific method: observe, propose, test, repeat. Again, I'm going to repeat this a lot. The scientific method here is a good way to keep you on track. Oops, sorry, went the wrong way. So use the scientific method. Read the manual if appropriate. Oftentimes you're writing the software. So read the manual should probably be changed to understand if you're using an outside class or you're using an outside methodology, understand what that's doing. What does that mean to read the manual? Well, maybe you're reading some Swagger documentation on an API of what's going in and what's coming out. So the manual is there, but read any documentation you can get. Now, often that's not there, but at least read it. If it's a problem inside your own system, there's no documentation, you're kind of on your own. But if you're trying to interface with, say, a third-party API, a lot of times they have documentation out there. And then this may seem counterintuitive, but make it fail. Make your program fail. It's hard to debug something if you can't make it fail. Now this can be difficult because oftentimes when you're developing software, you're developing it on your own laptop or your own PC in your own dev environment, which is different than production, and so you may have different tools or different setup. So make it fail. When somebody comes into you and says, hey, I've got a bug and this is what happens, don't say, well, it doesn't happen on my machine, because that doesn't help anybody. Make it fail. Find out why it didn't fail, and then make it fail. Second, the big one is look before I assume. Again, this is the difference to me between a junior, mid-level, and senior developer. One of the things, everybody can learn a language and code. It's those soft skills, and this is one of those soft skills. Before you assume what the bug is, and they may ask you, hey, we have this bug, what's the problem? A good developer will say, I don't know. I need to go back and look at it and come back and tell you what the problem is. a young developer, a junior developer, eager to please, will jump out and say, I think it's this. And so then they go out and assume that that's what the problem is. And then you have a tendency to get stuck in looking at that. And then if that's not the problem, you become frustrated. Good thing to say is, I don't know, I got to go out and take a look at it, and I'll let you know as soon as I can. Next thing here is this divide and conquer the problem. And this has really been helped with what they call agile methodology, in which you have a huge problem that you have to get solved, and you have a small amount of time to get it done in. So oftentimes, if you look at a bug and it's a huge bug, if you can divide it out, give it to other people and say, hey, can I get some help on this? Or here's some of the problem and it's affecting this and this and this. Oftentimes you'll hear, too many hands spoil the broth sort of thing. Not necessarily in programming. If you can find out that this bug's huge and needs to be cut down into different pieces, pass them down, tell them what the problem is and how to get them fixed, and have more people help you out. So, again, agile methodology, we use Git, which is a code repository. It allows you to isolate changes, meaning that you can take the code that's currently out in production and copy it to your local machine, and then you can take and fix those in an isolation, meaning you're not affecting the underlying code that's out in production. You're working on your machine. You're able to make those changes. You're able to use the scientific method, observe, theorize, test, etc., and make those changes to where you think you have a fix for that. And then you can do what they call a merge. You don't, if you can help it, let's just say, you don't ever want to change production code on the fly. My last job, that's what we did, and it's akin to changing the tire on a truck going down the freeway at 80 miles an hour. We can't stop the machine from rolling, but we got to fix these problems. And so you often come up with creative ways to solve that, making it more complex and getting back into the problems we were having before, in which now you've got this cobbled together beast that's going to cause more problems. Write down what I do in a debugging log. Now, you don't necessarily have to have a piece of paper and a pencil or write down what you did off to the side. You can often just comment your code. And not only comment your code, but you can also use comments like in Git for when you check the code in and out. So you check it out, you isolate your changes, you make it, you test it, and then when you check the code back in, you can put in there, this is the problem, this is how I fixed it. So it's a good thing to write down what you do. It helps you remember a little bit, but if you go back and look at it, you could say, oh man, I just made this change, and this change looks like it caused this problem too. So at least, keep some sort of a log. Now, this check the fuel level. The definition of insanity is doing the same thing over and over and hoping that it changes, and we've all heard that before. Oftentimes what will happen is when you become tired, you get into what they say, the weeds. You become less mentally acute, and you can find yourself kind of getting dulled down. And it's not bad sometimes to stand up and stretch, take a walk, go get a drink, do something, and then come back at it again. Nobody should ever expect you to sit down for 8 hours a day and not move. That you just can't do that. Get another perspective. You've been banging on this bug for a couple hours, and you don't see where the solution is. Oftentimes you can just hit somebody in the next cube or send a text, hey, you got a second? And they may come back and say, hey, not right now, I've got to finish. But they may say, yeah, what's up? And you could say, look, I've got this bug, I can't get it. I've tried, and the best thing to do is say, I can't fix this. The worst thing you do is say, I can't fix this. The best thing you can do is say, here's the bug, here's where I think it is, this is what I've tried, I'm just not getting a solution. Oftentimes someone can come back and say, well, have you looked at this or that, or this is what I have found. A different perspective can also be someone who's not technical. it's called in Agile, it's called rubber ducking. And some places you go, they'll have a little rubber duck that sits on your monitor, and you can stop and talk to it out loud. And oftentimes, talking to something out loud, whether it be a rubber duck or another person, through the course of the conversation, a solution begins to emerge. And I've seen this. At first, I was like, "Oh, that's garbage. I don't believe that." But it does in fact work, and I have had it work. You get talking, and sometimes I'm talking with somebody about it who's not technical, and they may say something that then, I'm like, "Oh, I never thought of that." You know, so get another perspective if you find yourself getting stuck. Then this big one: make sure the problem's fixed. You may say, "Okay, I fixed the problem," and then you send it out there, and they come back and they're saying, "We're still having the same problem." And this can really, if you get a reputation of saying it's fixed and then it's not fixed, then people will be questioning your code. They'll be questioning your ability, and it could be put you in a pretty bad position. So if you have the code and you have it debugged and you believe it's debugged, make sure that when you fix that and you put it, say, out into a staging environment, that it's still fixed. Often you will isolate your code, again, like I said, on your development machine, which may have different tools or a different environment. So make sure that it is fixed. And then I don't know. It says I will ask 3 questions. Well, it doesn't always apply. I mean, sometimes you know what the bug is. There's no reason to ask 3 questions. So I don't know. This one here, I was a little bit more of, just 3 questions. What if I have more? You should ask questions until you get the information you need to solve the bug. You don't need to ask a specific amount. So, Grace Hopper. This is a picture here, and I love this picture. And the reason why we call it a bug in software is because Grace Hopper found a literal bug in the software. And you can see here they had this software log. And as they were out trying to solve a problem, Grace Hopper pulled one of the vacuum tubes off, and underneath it was a moth, which was causing a short. When she took the moth out and put the vacuum tube back in, it started working. And she said, in that, "Hey, I found the bug." And that's where it stuck. And, but again, she was probably using the scientific method of what's the problem, asking questions, saying, "Oh, yep, I'll fix it," testing her theories, and in this case, it was removing, vacuum tubes. Hey, what's in here? Oh, okay. This one works. Push it back in. We still have the problem. Yes. The next one. Oh, here's the problem. So this is why we call them bugs to this day, thanks to Grace Hopper. So now we're going to go over these rules in a little bit more detail. And like I said, some of these rules I'm going to go in more depth versus others. But the first one I will. And it says I will own the problem. You will take, it says here, solving problems in the code he or she writes. It is more than that. It is solving problems in the code that you are given responsibility for. This definition of solving problems in the code that you write is not, in my opinion, really owning the problem. You take responsibility for the bugs that you either volunteer or signed for, whether you wrote the code or not. So owning the problem is not just saying that's my code, so I'm going to own it. It's I own this bug regardless of whose code it's in. Why? Well, it says don't look for scapegoats. It wastes time and energy. But not only that, it gets you a reputation as somebody who is not a team player or more willing to look out for themselves than to try to solve a problem. So, and then again, most common category of bugs are coding bugs, which I think is not necessarily true anymore. A lot of the development environments are really good now at helping find these coding bugs and bring them up before you even release the software, so that if you do miss a semicolon, it's going to let you know, or if you do call a method in the wrong way, it's going to let you know. So I don't think it's necessarily the most common category of bugs anymore. I I think what's important to understand about Rule 1 is regardless if you wrote the code or not, you're not going to blame anybody for it. You're not going to complain about it. You're just going to say, I own the problem. I will fix the problem. If I can't fix it, I will find a way to get it fixed. So remaining calm and the mental game of debugging. And I talked about a lot of these, so we're going to kind of go over these lightly because I talked about them when they were first introduced. But take a deep breath. Literally take a deep breath. I do like the recite a positive mantra. You don't have to sit there and repeat it over and over in your, and make a spectacle out of it. But do something that calms you down. Take a deep breath. Stand up, stretch, go look out the window. Be self-assuring. I can fix this. I'm a smart person. I know how, I'm confident in my abilities to do this. If I can't do it, I'll find somebody who can. Be positive. Do it, and it says calmly but patiently. Be very patient. Because if you start to lose your temper or your patience starts to slip, then all of a sudden you're going to find yourself not being able to do this in a rational manner. And it becomes an emotional manner. And solving bugs emotionally, is not the best way to do it. Use different problem-solving approaches that we've discussed. The big one, like I said, ask questions. Always ask questions if you get to a point where you feel like you can't go anymore. Somebody else may have had a solution, somebody else may have had a fix or a different perspective on it. Always, always ask questions if you find yourself stuck. Take a different path around the problem. Oftentimes that means getting up and to go along with, sleep on the problem, talk to somebody else, do some rubber ducking. Step back and say, okay, I've tried this approach and it's not working. Is there a different way to solve this problem? There's more than one way to skin a cat, as they say. Go out, look online. Go look at Stack Exchange or Google or Microsoft Docs if that's what you're using, and see if somebody else has a different perspective on it. Oftentimes you look at it and you're so sure what the problem is and this is the way to get it, you find yourself down this deep, dark path, and you're finding a good way to look at this is if you're finding a workaround to a workaround to a workaround, or you kind of stop and go, it can't be this hard. So again, this comes with experience, but don't give up. And like I said, sleep on the problem, or if it's not a critical bug, see if there's something else you can fix, and then come back to the problem. So I have to always give my spiel. I'm not a Thomas Edison fan. I'm more of a Nikola Tesla fan, because one thing that Thomas Edison did when he was inventing the light bulb is he blindly went forward trying to find filament after filament, because he didn't invent the light bulb. He was trying to find the long burning light bulb. Made the mistake of saying, I'll have a solution in 2 weeks. He thought he had a solution, which was a gate that opened and closed real quick to keep the filament cool, and then that didn't work, and then he just blindly went straight ahead trying to solve the problem. After the 2 weeks came and gone, and he hadn't filled out his promise, he hired some people who used the scientific method. The first things they did was looked at what was already tried, and then they, which Edison didn't do. He just did what a lot of other people did. And so he was so sure of himself that he was going to do it, and his confidence in his abilities, that he ended up just making it worse than it was. And so these guys came in, and eventually they tested, and they said, okay, that didn't work, and this didn't work, and they eventually came to a solution. So hopefully when they talk about the mental game of debugging for Edison, this was after that. In my opinion, Edison was more of a businessman than he was a scientist. But again, that's just, I'm a Nikola Tesla fan, what can I say? Anyway, they used the scientific method and then eventually got the light bulb to work. But what he would do is he would sleep through a problem. He had this metal ball bearing that he held, and when he'd fall asleep and they'd hit the floor and wake him up, and he claimed that's the answer that he was looking for. At least that's his claim. In real life, I think what he did is he may have realized that he overestimated his abilities, and he did one better in that he hired people, good people, to solve the problems, which is another good trait to have as well. So the scientific method, again, review the approaches for error margins. Straw man, I think, is a waste. But if you have a procedure, follow it. Otherwise, rule of thumb, ask questions. Observe, create, test, repeat. Again, observe, create, test, repeat. I'm going to repeat that because that sounds suspiciously like a test question that may be on the final, but it's also important to have. Going back to Thomas Edison, he didn't do these things. He blindly went ahead, often duplicating experiments that other people had done. Then he hired some people, I believe out of Princeton, and they observed what was already done. Then they created a theory saying this is what could work, and they tested it and it failed, and they wrote down their notes, and then they repeated it to the next one over and over until they found a solution. So that scientific method does work for software development as well. Read the manual. That's all I can say. If you're looking, like it says here, HTML definitions, read the manual. Often for development now, for C#, it's huge. It's a huge language. There's documents out there. Java's the same way. There's official documents. There's blogs. There's wikis, discussion boards, Stack Exchange. All kinds of places for you to find information on how to either solve a problem or understand the language. They say that manuals contain errors but have valuable information, which is true. Because one of the things about dedicating to writing a manual is keeping that manual up to date. And unless you're a large company with a dedicated technical writing staff, that often slips because you're moving on to your next problem and you haven't updated your manuals. But it still can be valuable in at least providing some information. But again, read the manual means go online and read the documents. They show the W3C here. Borrowed code. The difference between, again, a junior, mid-level, and a senior developer is you give a problem, a junior developer will say, I'm going to go out and I'm going to do this on my own and I'm going to reinvent the wheel. A mid-level developer will go out there and say, well, I'm going to use a little bit, but I'm going to still try to, reinvent the wheel or kind of keep it to myself. And a senior level developer, the first thing they do when they're given a problem is they go out and say, has somebody done this before? And if they have, what did they do? And, build upon somebody who's already gone through this before. At least that's my opinion. My boss and I talked about that, and that's kind of what the distinguishing between a junior, mid, and senior developer is. That senior developer says, has somebody done this before, and what did they do? Versus, I'm going to do it and reinvent the wheel all by myself. So make it fail. What can I say? Recreate it. Figure out how to make it fail on your machine. Don't ever say, well, it works on my machine, because that doesn't do any good to anybody, because they're not using your machine. Unless you're going to give your machine to everybody to use, it doesn't do any good to say it worked on my machine. Figure out how to make it fail. Determine why it failed. Use a stack trace. Get it in there, get it to fail, and maybe the solution you have is something you hadn't rolled out yet that fixed that bug. But you have to get it to fail. Something down here which is important is it is important to see when a bug does not occur. So if you do get the software and you put it on your machine and you say, well, the bug doesn't occur on my machine, then find out why it didn't occur, because that could be your fix. So it's just as important when it says to make it fail, is if it doesn't fail over here, find out what the differences are and what makes it so it fails here but not here. And then it says save all debugging tools for the future. A lot of the debugging tools now are actually built into the software. So some methods. Run the program repeatedly, making one change at a time. Start over and recreate the program. That to me is really not an option, unless it's a small program. But I want to talk about the first, the third, which is automate the process of running it and looking for external effects. So back in the good old days of 2012, Run the program repeatedly and make the changes one at a time. This manual testing, and this is why people didn't really test, because it was so frustrating and tedious to do. Okay, now run it, now change, this integer to a float, or change it to this, or change it to that. It became very tedious, time consuming, and eventually people said, I'm not going to do this anymore. So they wrote small batches to run it. But now, at least with Visual Studio, and I know with Java as well, there are testing tools that you can write what they call test cases that will allow you to read an external file for different values to put in. If it's an API, for example, you can use tools to automate the testing of posting and fetching information, so that you can write these tests once and then rerun those tests every time there's a change, so you don't have to take the manual testing. And it's a methodology called test-driven development, which some people try to adhere to. But writing test cases is a little bit easier than it used to be. So use those tools to make it fail, and keep those tools available, those test cases. Some places I've been in, if you write a program to release into production and you wrote these what they call unit tests, they all have to pass before that software can be released out into production, because those unit tests are designed to find bugs and to solve problems. And then, like I talked about before, look for external effects on the program. And I kept this bullet point on here, including user input. You may sit down and say, it works on my machine, and you sit down to the UI and you start typing information in and say, see, I can't get this to fail. But then you give it to somebody else and they may put a space, or they may capitalize something, or they may type in the number. You might expect only positive numbers, or you might be putting in 1 and they're putting in 0, 1. User input can cause bugs, and you don't find them because you know how the data is supposed to go in there. So oftentimes it helps to have a QA department, or if you can't get the bug to fail, go out to the person on the floor or wherever they're using it and say, show me what you are doing. That's a big key. Show me what you are doing. Then you can look at it and go, I see. They're putting their information in, and ask them, why'd you put your information in that way? And then you can possibly solve a problem without, repeating the same thing over and over and expecting a different result. Some big ones here. Don't assume that the cause of failure. And that bullet point up there, you may try to fix good point or code. That's what I was saying before. Oftentimes, a bug, when it is thrown, may not be the origin or the point of failure in that software. You may have to look at the stack or the calling methods and move back up that to find out where the true point of failure was. Otherwise, you're going to be down in where you think the code's at, because that's where the bug was thrown, and trying to fix all the code there when really the problem was further upstream. So you need to look at, when a bug is thrown, the best thing to do, and it's not in here, this says use print statements. No, use available debugging tools in Visual Studio and Java. When a bug is hit, you can also often go look at the stack. It's what they call. Remember in our file structures, we talked about a stack, and the stack is the last one on is the first one off. And so if you look at the stack, you'll see at the last point of failure. But you look past that and say, well, what was called here, and then here, and then here? You can kind of trace where this went through the program, and you can look at it and say, you know what, the bug wasn't here, it may be here. So use those debugging tools like this stack to kind of narrow in where the problem is, to focus your efforts so that you're not wasting time fixing good code. For debugging tools, it says use print statements. You don't need to do that. You can use what they call watches. You can put a watch on a particular variable and see what the value is of that variable. You can put it in and say, hey, it might be in a loop, for instance, and you might be looping through thousands of items, and you don't want to go through each line of code. you could put a watch on that variable and say, hey, break this code or pause the execution of this code when this variable gets to this value or is less than 0, for instance. And so there are a lot of tools available. Part of learning to program is part of learning to use the debugging tools you have available to you to debug your programs as well. Some other things in here, one or more copies for experimentation. This isn't really as big of an issue anymore, just because you have repositories, code repositories like Subversion or Git, which is really popular. You use Git and you could take a copy of that code locally and work on it locally, and then you can do what they call a merge later. But to have one or more copies for experimentation, then you're like, well, which copy am I using here? Generally, when you have a bug, you're going to pull a copy of the current production code, and you're going to pull it down to your local machine and work on it there, or a dev environment, depending on what the company does. You're going to work on it there. You don't need to make multiple copies anymore. Make a single copy that emulates what's currently in production and fix the bug there. Using descriptive naming conventions can often help, because if you get up and there's a variable that fails and its variable in name is 1, 2, 3, 4 or X, you may not know what that variable is, where the variable might be, instead of X, you could say discount shipping code. That can often give you a clue on where some of the problems can be as well. So divide and conquer. We talked about this. The big one, start with low-hanging fruit. What's the obvious problem? The obvious problem is well, the data is getting put in, it's not being validated. We're asking for a phone number and they're putting in an incomplete phone number. We're asking for a social security number and they're putting in, not just numbers, they're putting in letters. So there's some real quick things you can do. But then look at and say that bugs can cause other bugs. And it says here, they're talking, pretty low memory allocation problems can cause havoc, which is true. But you could have one bug that, for instance, social security number, and they put that in wrong, so that data comes in wrong, and you store it wrong, and then you try to run reports against it, for instance, and those reports don't work. So it can cause a lot of problems that way, as an example. So divide and conquer the problem doesn't necessarily mean with you, too. You might be able to come in and say, hey, there's some low-hanging fruit, or we have these problems that are residing in this module and this module. You can often get help from other people. So don't, you can only eat a whale one bite at a time. So if you have multiple people eating that thing, then it's going to, be less of a chore. So if possible, divide and conquer. Sometimes you can't, but when you can, pull in other help and get it done. So it's called Occam's razor, and we've all heard this. Often the simplest explanation is the right explanation. And so when you're looking at a problem and you're thinking, well, it could probably be this, and again, it comes through experience and knowledge of the language, but instead of trying to come up with an exotic solution to a common problem, look at it and say, if this is the problem, my social security numbers, for instance, have letters in them. Often the solution is, hey, maybe I need to validate that before it's entered. Don't bring it in and then say, well, I'm going to try to approximate that it's this or that or something else, so I'm going to run out and validate it this way. Keep it simple, which comes to the next one. Complexity finds making solutions difficult. And this I have run into, great example, working at Lifetime. There was one guy who wrote the whole shopping cart. He wrote the shopping cart instead of using established shopping carts because he knew better than anybody. And his solution was so complex that if there was a bug, he would often take hours to fix this bug, which would cause other bugs. If he had kept it simple, followed established, coding examples or something else, other people could have helped. It was horrible. The more complex the software, the more complex it is to debug. And then you can insert what they call breakpoints, and a breakpoint will pause the execution at a given point. And so if you're thinking, well, I think my bug is in this module, you could set a breakpoint at the beginning of that module, and so when the program's executing, it then stops. You can often step through each line of code individually and check what the variables are and the inputs and outputs. And that can also help you. I love the use test data, providing easy to spot patterns. Again, this is testing code. So let's say we're testing a method that is going to add two numbers together. And so you put in your patterns of negative numbers and a negative and a positive number and two positive numbers, and use these patterns, and then you start putting in maybe floats and then real numbers and then decimals, and then you start putting in letters. Put this test data in a way that you could see what the pattern is, so that when you identify the error, you're looking at it going, it's this kind of data that was failing, so now I have a better idea. So, it says create a database with similar but fewer records. Done this all the time. When we have database problems, we'll create a copy of the database and put in a couple of data points that are generally live data, and we'll run them through locally and see if there's a problem that way. Now my advice is, even though at my last job they would often test against production data all the time, don't ever test against production data if you can help it, because you might accidentally do truncate table or delete or do updates or all these changes which could affect live production data. So you should always have test databases and pull live data down to test with, but don't ever test against live data. So isolate your changes. The first thing you could do to isolate your change is to make a copy of the code and put it out onto your local machine. And then look at that stack. Use the stack and find out where the calls are being made from. You might have a huge program that's 300 meg, and you could technically start at the very beginning and trace it all the way through, but that's going to take you a lot of time. Use the stack and try to narrow in on at least on a starting point of where you think the bug may be, because you're trying to change the fewest amount of code as possible. It says compare version. In Unix it says use the diff command. If you're using something like Subversion or Git, at least in Visual Studio right now, if there's a module you're on, you can right click and say show history, and it will compare your code to the previous version of the code, and you can see what the differences are, and you can say, somebody put in this line of code for some reason which caused this bug. Isolate your changes by pulling them down to a test environment that's not affecting production. Use the diff command on Git. Use the stack to find out where you think the problem is, and start kind of looking at it as, you may take a guess and say, well, the problem might be here. So you put a breakpoint there, and you run to that point, and it runs just fine. And then you say, well, it's not here, so you move the breakpoint, and you continue to move it until you finally get to your bug. Again, this is being familiar with your development tools and the environment that you're in, but you want to isolate those changes. Take a single bug out of a 300 meg program and narrow down quite quickly where you think the problem is, instead of starting at the beginning. Otherwise, you're just going to have a long, frustrated, tedious task of trying to find out exactly where the bug is. When it says to use a debugging log, if that helps you, that's great. But when you're using these control, like Git or Subversion, these code versionings, my suggestion is that when you check in code that you made a change, that you put some details in there and say, I'm fixing this bug, and this is what I did in this solution. Now, what's really kind of nice, if we go back here on the isolation of changes, if you don't put in a comment, you can often go back and say, what's the difference between the code that I had before versus the code I have now? And you can often just infer from the code that they were fixing a bug, and you can see what changes they made. But it's still a good idea, and not only to comment the code or the changes you made because you need to let everybody else know, but by you making those and writing them down, it helps kind of put it in your brain a little bit as well. use version control software. This I love. Keep it in here. It's called SourceSafe. Man, that was old stuff. Version control software. Subversion is a big one, but Git, G-I-T, is probably the biggest one out there now. You even if you're doing your own programming in your own house on your own computer because you're going to write the next greatest, biggest software, you should use Git and a website called GitHub to store your code so you can version it, so you can see the changes that you've been making, keep track of different versions. I mean, not just for debugging, but now you've got somebody else who wants to help you. They can pull your code down and work on it too, and you can both work on it together. I do not suggest manually recording a version in a text or spreadsheet because as your program becomes more successful, you're not going to take the time to do this, and then pretty soon this text file or spreadsheet is out of context, out of sync. Now remember, if you commit to writing software manuals, you have to commit to keeping those manuals updated as well. So use the version control software and document your changes in there. I know that in Git you can require that if somebody checks something in, they have to have a comment. You can't necessarily control what they put in the comments, but they have to have a comment. Oftentimes there's tools that will link a bug that you're tracking to that, so when you check in the code it will automatically pull it in and give you some more information as well. Electronic logs can be shared, and when it says write down the changes in order, oftentimes you can find out that the changes just by looking at the code. Look at the previous version, but sometimes in your comment you can say, hey, I fixed this bug, which fixed this bug, which caused this problem, etc. So this is a kind of an example of a log that maybe was something you could put in as you're checking your code in and out of Git. So what did I do? What program? What happened? This I'll be honest, 20 plus years I've never seen this happen. What you may say is, what did I do? You might have a bug out there that says, when somebody puts in this value, this bug happens. You already know what program version it is because the software often keeps track of the program version for you. And you will come out and you will say, you don't need to say I needed to add a breakpoint at line 30 and line 15 in these different versions. This is, unless there's a requirement by the company, this is just going to really take a lot of time and effort, and you're going to spend a lot of effort doing this and having to maintain it. Generally what you're going to do, I would say, is you're going to pull the code down, you're going to find and fix the bug, you're going to check the code in, and on the check-in, you're most likely going to say, found a bug, that was, you might be kind enough to say, bug number, 1234 in this sprint, changed it from this value from here to here, and then check it in. Now, even if you don't do that, somebody could still go in and look at the previous version doing a diff and see what was changed and infer what was going on. So I don't necessarily adhere to the Rule 9 here of going through all of this information. You might do this if you're maybe writing an assembler or something along those lines, but now most of the version control software does this automatically. So the what did I do would probably be valuable in the notes of checking it in. What happened? Program didn't crash, but output was delayed, or etc. As you're debugging something, if you had to write down every single change that you made and every single what happened, you're going to be spending a lot of time doing that. Generally, you're going to get a bug, you're going to identify the bug, you're going to fix the bug by doing a lot of these iterations, and then when it's done, you're going to check it in and say, I fixed the bug, it was in this module, and move on. So, the reasons to record information is in here. I don't know. I kind of look a lot at this now as a waste of time. Again, it's my opinion. But when it says it works on other people's programs or works in their environment, we talked about this before. In that if it's running on yours and not someone else's, look at what data they're putting in or look at what the differences are when you have your your operating systems. What's the difference? Sometimes that is the bug. Um, Running on different operating systems, again with C Sharp and Java, is less of an issue. They've really gotten this down with .NET Core, at least, being able to run on Windows, Mac, and Linux. Fairly straightforward. They have programs out there like Xamarin, for instance. Xamarin Forms will allow you to run on Android and iPhone and Windows. They do all the translation for you. And so there's a lot of tools in place that help with this now. And then this last one I want to take a minute on. It says programmer may not have documented well. It is well known that you could fix a bug and know what's going on and come back 6 months later and go, I don't know why I did that. I can't remember what I did that. For a number of reasons. The person who was asking to make the change may have left the company. The company could have shifted directions. There was something going on at the time that this was an adequate fix. Don't rely on your memory, because as you do context switching to other programs, you're going to find that you're going to go back and look at code 6 months later and go, wow, what was I doing? Why was I doing this? So it's not a bad practice to comment your code. Now, there are other coding practices that are outside the scope of this class on keeping your code simple using what they call solid principles. But if you're not afforded that, make yourself a note. Put something in here if there's a reason for it, and put out there and say, talk to so and so, and we had to do this because of this customer. That might be enough to jumpstart your memory. And then we talk about commenting code, and we'll talk about this later. Well, how much comments do I put in there? Well, you put in a number of comments that you can assume that you will not be working on this code again, that someone coming behind you is going to be working on it. So give them information saying, hey, fix this per this bug number, and then they can go look up the bug number in some sort of bug tracking program to see what's going on. So I love check the fuel level, meaning most likely problems. Not necessarily syntax errors; those really aren't as big a thing anymore. But look at the logic problems. I would say before you even get into the compatibility issues, which isn't a big thing, or architectural problems, then in here you should have your coding, your logic. Go back and look how the program's being used. What's the data being entered? Am I missing some validation? Again, that falls under the logic problems. But before you start going down into compatibility and architectural problems, which can lead you down a rabbit hole, start simple. Syntax errors you'll probably know. Look at the logic problems. What's this program, what's this bug really telling me? And then look and see, is the data correct? Before you even start making changes. And then make sure that your assumptions are correct. Make sure that the version of program they're running on is the correct version. They may be running 2 versions older. But these are small things you need to look at. Now, hopefully they're all running the same version, but if you have external clients and they haven't upgraded yet, first thing to do is look at that version and say, well, that's an older version. You need to upgrade first. So before you even start going in and looking at bugs or solutions or fixes, make sure they're running at least a correct supported version of the software. And then make sure your debugging tools are working correctly. At this point, I assume they are. I have no way to verify that my debugging tools within Visual Studio are working correctly or not. I just have to assume that they are. Now, another thing under check the fuel level is make sure that you yourself are not burned out. A bad time to program or to debug always seems to be late in the afternoon on a Friday when you're thinking about what you're going to do over the weekend. If you find yourself your mind wandering and you're not necessarily concentrating as much, get up, stretch, go get yourself a soda or something, sit down and do something else for a couple of minutes to just kind of, reset. Getting another person's perspective, I cannot stress this enough, especially for junior, mid-level developers, again, for everybody. But, if you have a bug, try to identify it yourself, of course. Own it, like we talked about, and try to identify it. But, what's the rule of thumb? I don't know. But if you don't, if you've extended what you think or exhausted what you think is your abilities to solve this problem, then stop and ask a question. You know, it may be rubber ducking, as we talked about. Give a sounding board, bounce ideas off other people. And that's why they're talking here. Talking out loud will solve problems. Bringing in somebody else who may not be technical could solve a problem, So don't sit there in frustration, ask questions. Now, my advice, though, is just don't go and immediately ask a question. Try something first. As a senior developer, if I've had somebody come to me and say, well, I can't fix this bug, the first thing I'm going to say is, well, what have you tried? What do you think the bug is? Have you identified it? So make an effort, say, this is what I think the bug is, and this is what I've tried, and I just can't seem to find a solution. It's going to go a lot further than I have this bug I can't solve. Now, hopefully you're working in a place where people are willing to help. But that last one, report exactly what's happening. Stick to the facts. Now, when it says do not present theories, I don't think that that's necessarily a bad thing. What you should do, though, is say, here's the bug. Here's where it's happening. Here's what I've tried. Here's what I thought it was. And here's my theory on maybe what it is. So it's not bad to propose a theory, but remember, going back to the scientific method, you've got a theory, then did you test it? It's great to give a theory, but did you test that theory? So what you should say is that this is what I've tried, this is where I think it's at, and now I'm kind of stuck. Because, coming to me and saying, hey, I got this bug I can't fix is, I'm going to immediately ask you, well, did you identify it? What have you tried? So check the problem that's fixed. If you work in a company big enough to have a QA department, you fix it, you run some unit tests, maybe some regression and integration tests, but then you send it out to QA and they look at it to make sure that you got the bug fixed. So don't assume that you fixed a bug and you haven't tested it and send it out there. Always test it. Now, the second bullet point up there, bugs do not go away by themselves. This is, to me, the scariest bug. It says if a bug seems to resolve itself, then something has changed, and that bug's either going to come up or you've got a bigger problem. Bugs just don't magically disappear without some action on them. So you need to make sure that the problem is fixed. The bug itself may not be in the software, it may be in the environment, and the change to the environment fix the so-called bug. But you need to make sure that it's fixed. If you can't, now it says track bugs that can't be fixed. Well, let's talk about that for a minute. All bugs can be fixed. Theoretically, they can all be fixed. But bugs get priority. And some bugs are a nuisance, and some bugs people can live with. Some bugs are more critical. So when it says track bugs that cannot be fixed, I would say track bugs that can't be fixed right now or don't have a priority. Because I believe all bugs can be fixed. Even if the fix for the bug is a workaround or turning a feature off because the software won't, the operating system won't support it or something along those lines. But you could still fix it. So make sure that when you send that out the door that you've done adequate testing on it so that you're confident that the bug has been resolved. Because nothing is more embarrassing or nothing damages the reputation of IT more than to say, I fixed a bug and then it's released and that bug's there, or the bug's there and now another bug is there. So you really need to make sure that what you're pushing out the door is in fact good software. And then ask 3 questions. And I talked about this before. There's actually more than 3. But these 3 questions. Is this mistake occurring anywhere else? Now, it's not a mistake. It's a bug. Is this problem occurring anywhere else? This next question to me is the stupidest question. What next bug is hidden behind this one? Well, if I knew that, then it wouldn't be hidden. So the better thing to say on here is not what next bug is hidden behind this one, is is this bug causing other bugs? Or could it be potentially causing other bugs? And it may be nothing more than a cursory glance to say, well, this data is going into the database. Let's go out to the database real quick and look. But to say, what's the next hidden bug? Well, if you knew what the next hidden bug was, why didn't you just fix it? So to me, you can't see me now, but I'm just shaking my head. It's the dumbest question to me. But how can I prevent this bug? Now, this is a good question. So you fix this bug, and if you don't learn from it or find out how to, prevent it in your coding, you're just going to continue to get those bugs. So if you get a bug, for instance, on an array that keeps going out of bounds in a loop, maybe next time you write a loop on the array, you're going to use the counter of the array items so that you never go above those items. This is part of just learning from your coding mistakes. So these 3 questions, it's really 2 questions and one that I think is really dumb. A couple other questions I would ask on these bugs while you're looking at this is, how can this bug be prevented in other systems? Meaning you might be using a bug, or you might be using a method in your software that they're using somewhere else in software, or you might be, how can my software prevent bugs from external systems from affecting my system? Is another good question to ask. You may have data coming in from external parties that you are getting, bad data. And so you need to capture these bugs, or you need to validate your data so that these bugs don't come into your system. So there's a lot of questions that you can ask, but asking what the next hidden bug is doesn't ever make any sense to me. So a couple of things here I'm going to go over to see the rules in action. So a student asked why his picture wasn't showing up on his web page. Happens. Tried the web page on the PC and it worked. So he loaded the page on the server we're using. I asked, where's the picture file? Okay, first question right there. Where's the picture file? So he says it's right here on my computer. And I said, well, it needs to be on the server. You upload it, it still can't display it. And this one is an environmental issue because you'll notice it's running on Linux. Let's assume he was, running it on Windows. It says it's on his PC, so they changed it over to Linux. Linux has a case-sensitive file system where Windows does not. And so, he's using Windows and, it doesn't care, but in Linux it does. So now, he changed the spaces to underscores in this case and upper to lowercase, and found out that Linux was case sensitive and they got it to work. So how did they solve this in here? Well, instead of tearing into the web page and start looking at code and going off about all kinds of different like frameworks or JavaScript or compatibility, they stepped back and looked at it and said, what's the problem? Well, the first thing is that needed to be on the server. And then I like this one here because it's like, oh, it just needs to be on the server, and assuming it's fixed. So they put it on the server, it's still broken. So then they looked at it more and saying, well, it should find it. Why isn't it finding it? They found out that our environments were different, and the different environments were causing the bug. It wasn't the underlying software. It was the underlying environments, Windows to Linux, these naming conventions. So you can see here that this bug, you could have spent a lot of time trying to fix good code when all you had to do was observe what the problem was and say, we have a fundamental difference between Windows and Linux, and here's the problem. So again, review the rules of story number 1. I like the way that this was presented because it's showing that you don't always assume a bug is in code. So rule 2, working on a program, wondered why the variable wasn't changing. First key, I was new to programming in PHP, so I assumed, that's the word, the variable scope was the same as other languages I used. It's a common misconception, saying, hey, this language, I assume this is how it works. And so he kept banging away at it. Mistake number 2. changing different parts of the program, trying to figure out what was going on. Again, not understanding the problem, so they were changing good code. So you're new to a language, you make an assumption, and then when it fails, you start banging away at good code. Finally, they asked somebody, and they found out that, and I know I like this one because the colleague said, hey, why don't you go look up the variable scope for PHP? Instead of telling them the answer, says, sure enough, my assumptions are wrong. 5 minutes of looking up information solved a problem. So, again, a couple of keys here. Using a new language, and the biggest thing, if you find yourself assuming that this is how it works, that's a red flag for you. And then they spent 45 minutes plugging away at good code instead of just stopping and asking a question. So again, don't be afraid to ask questions. This one decided to write a little client-server game as a way to learn about sockets. Sockets are what you communicate with through TCP/IP. Based on what I read, again, first red flag, I assumed, again, the process would go like this. I send a message, it responds, I'm here. Send a message, here's the work to do, and it responds with working or here's the answer. However, it didn't work that way. The server responded with one message, I'm here, and here's your answer. Now, it appeared to be working the way I assumed it should, but the response didn't match what I read in the manual. So I had to experiment. Again, assume. It says it didn't match what I read in the manual, so at least they read the manual. So I had to experiment. Well, maybe that manual's out of date. So again, assuming is that first red flag when you say, well, I assume. Now again, assuming is not a theory. Theorize this is the way it should work, then you test it, then it doesn't work, remember? Then you observe it and theorize and change and test, etc. Had to write an ASCII program for converting file types. Worked flawlessly, so I took it to my boss. He gave me a 2.5 gig file. It didn't work. Took a while to realize that the file was too big, and then they had to rewrite the program completely because no one told me the program had to handle such a large file. Okay, of course we're both at fault. I should have asked, but my boss shouldn't have told me. This violates the number one rule. I will assume ownership. Okay? There's another thing in here is they never asked what the file sizes were. So this person then had to rewrite it because they didn't ask questions saying, what's the scope? How big are the largest files going to be? That's a mistake everybody makes. Getting excited, get some code down, not having your requirements. But the biggest problem in story number 4 was, of course, we were both at fault. I should have asked, but my boss should have told me. That is not taking ownership of the problem. And I can almost guarantee you that if you fix the problem and come back to him and go, you were at fault, you didn't tell me that it was going to be this big of a file, so this isn't all my fault, it's your fault, that is not going to go over very well. In fact, the boss may come back and say, you never asked. So it never does well to get into a blame game, ever. Because then you start pointing fingers, people are professional. Just go in, give the boss back his file, saying, sorry, I just assumed, your files were only going to be this size, so I rewrote it, I learned I rewrote this. And then move on. Don't ever play the blame game. You're not going to get anywhere with it. Mom called me and complained that she couldn't enter her password for her email account. Right? So this is something that's common. Question was, can you enter your text anywhere else? Turns out she couldn't. My next thought was her keyboard wasn't hooked up. Right? It's a safe assumption to make. I knew she had a wireless keyboard, so I told her to reset it, and if that didn't work, try replacing the batteries, and it worked. This is a very good methodological standard way of doing this. Instead of saying, oh, your keyboard's bad or your computer's bad, you need a new motherboard, your I/O, you can see how you could easily assume all of these. But instead, this person took a very methodic approach. Can you type anywhere? No, I can't. Okay, well, now you know it's probably the keyboard. So, they looked at it and it's wireless. So they're, okay, hit the reset button. Bluetooth often loses. No, it doesn't work. There's no lights coming on the keyboard. Let's change the batteries. And all of a sudden it starts working again. But they could have easily torn apart the computer and tried looking at the motherboard or went out and bought another keyboard. There's a lot of things they could have done. This is Occam's razor here. What's the most simple problem? Is the keyboard not working? No. Reset it. Doesn't work. Well, let's try batteries. But the big thing in there is, was the keyboard hooked to the computer or not? So again, instead of going off on a wild goose chase, often the simplest problem is the solution. In this case, it was. So a couple last thoughts here. This is to post them near the computer, and I say that's not necessary. I would say out of those rules, the biggest one that will get you the furthest, that will probably land to a good career in computing, is I will own the problem. That is the one that is so important. Own the problem. Everything else will come with experience, but I have known senior level developers who have been programming a long time who will never own the problem. They'll fix it and complain about it. I will own the problem. So, in the debugging world, know that it's mind over matter. Be confident that you can fix these problems. Any bug can be fixed. Just be confident you can. Stay positive. I can't stress that enough. You can find a solution either by yourself, go online, ask some colleagues, but assume you're going to solve the problem. Use some of the techniques in here. Walk away, talk about it openly, rubber duck it, whatever you need to do. But just assume that you can always solve a problem. So, to wrap this chapter up here, it looks like we've gone about 2 hours. Again, you're solving problems. That's what you do as a developer. That's what I do as a developer. Computer or the company comes in, their problem may be they want to get more money in the door. They may want to expose themselves to more companies. There's always a problem that can be that you have to solve. Otherwise, you're coding. I'm just going to write a hello world program. You're solving a problem. You're trying to do it the best way that you can. Use the scientific study or the methodology. Observe, theorize, test, repeat. Okay? Until that theory can stand on its own. Stay positive. This is like the 5th time I've said it. Stay positive. Know that there's coding bugs, which is really being taken care of by and they're called syntax errors as well. Most of the development environments will let you know of syntax errors. The big one is the logic bugs, and those can range from something as simple as I need a phone number and somebody's putting an O instead of a 0 or validation, to something extremely complex with mathematical formulas running real-time simulations. It's a logic bug. Bad data bugs, this is what you do for transformations or validations. You put in your code, as we'll talk about later, error trapping to account for conditions that you can't possibly meet. There's ways around this. Compatibility bugs, less of an issue but still relevant, meaning that your bug, and I air quote that, it's kind of hard to see, in compatibility issues may be that the windows look slightly different, or the GUIs do. And then architectural bugs, and that's a huge, that one's huge. This is what I'm talking about. Writing a program that's a proof of concept that gets released out into production and is a bolt-together Frankenstein. And then all of a sudden, every time you make a small change, it's like an earthquake and it affects many things. It's architectural bugs are very difficult to overcome without re-architecting the solution the right way. And oftentimes, though, it's not necessarily bad architecture. It could be antiquated architecture as well. So why is it difficult to debug? We talked about this, the fog of war, multiple goals, people wanting different things to happen. The complexity because of multiple systems or bad architecture, or the big one here, constant change. Remember, before you start coding, really, as hard as you can, make sure you can get a set of requirements to develop to so that you have an end goal in sight. Constant change is frustrating. You spend a lot of time wasting a lot of code. When I was at Motorola, we had meetings and the code, the requirements were literally changing every hour some days. It was so frustrating because you just can never get anything done. So try to get a base set of requirements. Know that there's the 3 problem-solving approaches, the straw man, which is horrible, of throwing something out there knowing it's going to be torn apart just because you feel like you have to contribute. The big one is the rule of thumb. Not everybody has procedures to follow. So the rule of thumb, heuristics, is a good place to start, and that comes through experience and time. Again, scientific method. I'm going to repeat it one last time. Observe, propose, test, repeat. Test questions. This is a good base to put your debugging on. Observe the bug, propose a theory, test it, and repeat it until it's strong enough to stand on its own. That is really a good scientific, disciplined approach to doing debugging. Then there were the 13 rules of debugging. Some of those were good, some of them were meh. Again, that first rule, I will own the problem. If you own the problem, I think the other 12 rules will probably fall into line. Because if you're going to own the problem, you're going to be willing to go get help. You're going to be willing to find a solution. You're going to be willing to go out and be positive because you know that you're a smart person. So again, you'll own the problem. And they say print them out. If you want to, print them out and use them as guidelines. But if not, just remember, I will own the problem is the biggest one. So that's the end of this recording for the chapter. And if you have any questions, again, put it out on the discussion forum and or email me directly, and we'll see what we can do about getting you a solution.